Hi, welcome. So what we're going to talk about in the next two modules is about skin friction drag, right? So I think one of the reasons why we are studying boundary layers and its effects, as we started out saying, is that it causes drag, right? And we need to, quantify that how much, given a certain size of the surface on which a fluid is moving, what kind of drag that can cause. And I think we use some results of boundary layer theory directly, without going into the derivation of it. Skin friction coefficient for a laminar boundary layer. We used formulae and used a problem to kind of solve that. We're going to sort of just learn a little more about that, and a very interesting way of calculating the drag. And if you have access to very simple facilities anywhere, you can actually set up an experiment and do this yourself, and it can be quite interesting. Okay, so let's just try to understand what we mean by drag. Okay, a little more about that. Okay, so what basically we're going to talk about is, let's write that down, saying that what we're going to talk about is essentially skin friction drag, right? This is what we've sort of started out saying we will do. Okay. Now, for example, now I'm going to draw a couple of scenarios. Okay. Now look at this. Look at this scenario. Okay, this is an airfoil. Well, actually, just now let's get that out. Okay, let's look at this. I'm going to draw that a little differently. Okay, that. Then I'm going to have another scenario which is like that. Okay, and yet another scenario which is like this. Well, this is a little more thick than I would like it to be, but So now these are basically three, cases. Okay. Now what we're going to look at is, and what we basically have here is that I have fluid moving this way. This is the free stream. In all the three cases, this is the free stream. Okay, this is the free stream. What I can do here is, for example, draw the pressure distribution. Okay, draw the pressure distribution. Okay. Okay, I have a pressure distribution like that. Okay, what about the pressure distribution here? Something like that. Okay, and similarly there is a certain pressure distribution this way. Okay, something like that. Now, so basically this is the pressure distribution. Let's say if I were to write this, this is pressure distribution. I'm going to write this is very important here. I'm going to say this is basically on lifting surfaces. Okay, lifting surfaces. Okay, now this one, as you can see here, this is actually a cambered airfoil. Sorry. Right, this cambered airfoil, and as you can see, the angle of attack is actually 0. But this is going to lift, because there is a differential pressure distribution on the upper surface and the lower surface. This is the upper surface, this is the lower surface, right? This is a symmetric airfoil, okay? This is actually a symmetric airfoil, and here angle of attack is not 0. There is a certain angle of attack. Okay, how do we calculate the angle of attack? Well, I think that's basics, but I will still talk about that here. Okay, let me come to that. So symmetric airfoil, this is alpha is not 0, and this is essentially a flat plate. Okay, and here too alpha is not 0. Now, of all these three, basically the symmetric airfoil and the flat plate will not lift without an angle of attack. So, in this particular case, it does have an angle of attack. The cambered airfoil, however, due to a shape, as you can see, it's different from this airfoil, okay, it will lift, even at 0 degrees, okay, because due to its shape, the differential pressure is created. Okay, so what do we mean by angle of attack? Okay, so what we're going to do is just join the shortest points between, this is the leading edge, right? So this is essentially the leading edge and this is the trailing edge. And if I join that, sorry, that should be a straight line, okay. So if I join that, if I join basically the the leading edge and the okay, I need to get a straight line here. Okay, now I need to get a straight line, so okay. Now, so this line, which joins basically the leading edge to the trailing edge, right? Just this bit, right? This is the chord length. That's the chord, right? And the angle that this chord length makes with the free stream basically gives you the angle of attack, okay? So, if I were to sort of take that off here, and say this, so this is your free stream, right? Then this is your angle of attack. Okay. Similarly, you can explain yourself for a flat plate. Now, basically the three pictures that I've drawn here, all of these three things will be able to cause lift, which is great, right? And primarily the way we now the question the next question you should be asking or thinking about that, okay, but which will cause more lift or which will cause less lift? How much will each of these lift? Okay, I've got a symmetric airfoil, I've got a cambered airfoil, I've got a flat plate, so which one will lift more? Well, that is something which will be given by when we quantify lift, and we quantify the lift. And how do we do that? Because what we do is we integrate the pressure, right? We integrate the pressure over the surface and take its component in the lift direction. So I will come to what the lift direction means in a bit. Okay. Okay. So basically, the lift direction essentially is a direction which is perpendicular to V infinity. Okay. So in this particular case, so if I were to do that, so say here in this for this camber airfoil, my lift direction will be this is going to be lift, right? And actually this is going to be lift and this is going to be drag. So drag direction, that always acts opposite to the free stream, right? And in this particular case also, it's also so the lift and drag in this particular case, because this is my V infinity is horizontal for all the three cases, as you can see. Therefore, the directions for the lift and drag, this is lift and this is drag, because this is your V infinity. Okay. So okay. Now okay. So now the thing is, so therefore basically you can you can see that we're not talking about any sort of boundary layers or friction or anything like that, right? So therefore lift, right? Lift can be calculated, okay, fairly accurately using inviscid theory, right, along with kata condition at the trailing edge. So if I were to write that, so lift can be accurately calculated, right, using inviscid theory, okay, plus along with, okay, plus kata condition. Okay, at the trailing edge. Now, I am not going to explain too much about the kata condition, that is beyond the scope of this course. Let me just say that what the kata condition basically means, it basically enforces numerically the fact that the flow leaves the trailing edge smoothly. Okay. So, if I were to basically draw a streamline past this, it's going to leave it smoothly. Okay. Now, that is yeah. So, basically otherwise, there is a possibility that you would have a different value of the circulation on the top and the bottom surfaces. You wouldn't want that. Okay. So, the kata condition is basically that it enforces that the flow leaves smoothly at the trailing edge. Okay. So, I am going to leave it at that. So, therefore, lift can be accurately calculated. However, okay, if you want to predict drag using the same theory, okay, using the same theory, it results in zero drag. Okay, this results in zero drag. That's because if you do the integration, if you think about it, right, on a closed surface like this, right, so the components kind of cancel out, and let me see if I can sort of draw this. Okay. Okay. So, for example, I think you should be able to sort of do that yourself. For example, if you look at this flat plate, okay, and I'm looking at these two arrows here, so this is arrow 1 and this is arrow 2. I'm going to draw the components, okay. So, one component is going to be like that, the other component is going to be like this. So, basically components with respect to this this axis system that we are looking at, right, in the lift direction and drag direction, let us put it that way. Okay. So, that, and in this case, if you see, if I take the components, it is like that, right. Now, if I do this, now what you will see is that in this particular case, say this is say D1 and this is D2. Now, if I do a summation like this, right, these will cancel each other out, right. These arrows which basically indicate pressure direction, right. So, therefore, if I use this principle, where I can accurately calculate the, the lift from inviscid theory, it does not necessarily result in any drag, it actually results in zero drag. Okay. So, if I use basically inviscid theory, it results in zero drag, right, and this is, it's not possible, this, anything like this, by now, we've talked about boundary layers for some time now, that it's not, it's a physical impossibility, and therefore, this is what is commonly known as right. It's known as D'Alembert's paradox, right, after Jean de D'Alembert, who is a French scientist. Okay. Now, however, this paradox immediately goes if you're going to use a viscid theory, in the sense when you do not ignore the boundary layer, when you do not ignore viscosity, right. So, if you take viscosity into account, this paradox is completely gone, right. And therefore, one can really say that viscosity is solely responsible for the entire aerodynamic drag on a lifting surface, right. If I were to write that viscosity, right, is solely responsible for the aerodynamic drag on a lifting surface, right. Now, it is, right, and then again this has two parts to it. Okay. Let me write that. So, therefore, this drag, then I am going to classify this right a little bit. It has the drag, again it has two parts to it. There is the skin friction drag. Okay. This is the skin friction drag. Okay. And this is due to the shear stress acting on them. So, the skin friction drag again, right, this is due to shear stress acting on the surface. Okay. And the other is basically pressure drag. Okay. The other is pressure drag, and this is also called foam drag, yes, and this is due to the pressure created during flow separation, right. So, this is also called foam drag, right, due to flow separation. Okay. So, basically we are looking at two types. Okay. We have described this. So, it is skin friction drag and pressure drag. So, let me just sort of explain that a little bit. So, what I mean is, so I have got this surface, right, So, this is say and effort. So, how does that look like? So, we know that, right. So, this is wall shear stress, we have been doing this, and that basically is acting along the surface. So, this is your sorry. So, then okay. So, then we've got so wall shear stress, okay, again, right. So, again here on both surfaces, and so on and so forth, okay, you get the idea. So, basically this is the wall shear stress, right, and this is what causes skin friction drag, right. This is, yeah, you can think of this as basically the flow dragging itself, because dragging itself on a solid surface, because the flow is basically trying to move and the solid surface is trying to pull it back. So, the flow drags itself, that's what is basically, it's kind of forcing itself, right, on the surface, and that is basically this skin friction drag which results in skin friction drag. Okay. On the other hand, let's say you have this again, okay, and now you have flow, okay. So, you have okay, so okay, that's not right, not to be inside. So, this is a separated streamline. So, you've got stuff which is going on top. These are streamlines, right. So, then there is sort of backflow of the pressure, etc. Now, this results in what is known, what we just discussed as pressure or form drag, right, pressure or form drag. Now, what we're basically going to now, so basically our job is that we would like to quantify, right, given the size and shape of some body, we would like to quantify that, we would like to find out how much shear stress and how much pressure or form drag a body is going to cause, right. Now, before so there's a very simple and very interesting method of doing that, and what we're going to do is basically we're going to use the momentum equation, okay. We're going to use the momentum equation, right, to evaluate this drag. Right. Okay. So, how are we going to do that? Well, what we're going to do is, let me draw this, I'm going to draw a control volume using actually the momentum equation. This is actually a application of the momentum equation, and we're going to draw a control volume around a flat plate. Basically, we're going to try and understand a flat plate. Now, let us look at a flat plate. So, let this be the flat plate. Okay. And okay, so let's look at the flat plate like that, and then I'm going to draw so this is this is somewhere here, and this is somewhere here. Okay, and these are the two locations. When I'm going to have to confine a boundary somewhere, right? So this is the boundary that I'm looking at. Okay, and okay, so essentially now this one, these are almost going to be straight lines. Okay, these are going to be almost straight lines. Okay, and you see that I have two, you know, gaps here, which is about right. I am taking, you know, the gap. Okay, now, well, this is going to be a straight line. Okay, please bear with me. Okay, I'm drawing it's sort of this, but it's going to be straight line. Now, what? So this is the thing. Now these, let me first name these. Okay, now I'm going to call this as A, B, C, D, E, F, G, H, I. Okay, so what we so this is my control volume, and what I'm going to do now is going to draw the velocity profile at the inlet and the outlet. So you, by this time you know that this is kind of inlet, and this is AI is inlet and BH is outlet. So here is nothing. So there is free stream which comes in. Okay, so I got that. So I got that. So this is my velocity profile. Right, and I'm going to call this, essentially this is, let me say this is U1, right, and that is equal to the free stream. So let me say that this section is essentially 1 and this section is essentially 2. And the free stream and the velocity profile here would look something like that. You know, we know that already, right? We know that already. Something like that. Okay, and let's call this as U2. Let's call this as U2. Now AB, right, and IH or HI, whatever, these are like really far away from the body. Okay, these are really far away from the body, and this line is basically a line which is just sort of inside the streamline, okay, just inside the streamline, in the sense that there is a streamline which is just outside of it, right? There is a streamline which is just outside of it. Similarly at the bottom. So these boundaries are just inside the streamline. So therefore this is a streamline. Far from the body, right, where it's basically free stream pressure. Okay, so what we'll do is we'll kind of stop here and continue with this in the next module. Okay, thank you.